Let's assume that f prime of x exists. Let's assume that our function has a derivative. What I'm going to show is that the function must be continuous. Which is to say that if you have a derivative, then you have to be continuous. Which is to say, if you're not continuous, you couldn't possibly have a derivative. Okay, so we're going to assume f prime of x exists. We're going to assume we have this limit. And what I want to look at, rather than this limit, because we know this exists, we're assuming it, let's look at this limit, which is the limit that expresses continuity. In order for a function to be continuous, this limit has to be 0. So let's consider the limit as h approaches 0 of f of x plus h minus f of x. We want to ultimately show that that's got to be 0. And here's what we're going to do to make that happen. I'm going to take this thing, which is a perfectly valid mathematical statement. It's a limit minus another thing. It's just subtraction. And I'm going to take whatever this result is, I'm going to multiply it by h and then divide by h. And this is fine because while h is approaching 0, you know limit is all about approach. So h is going to 0. H is not going to be 0. H is just going to approach 0. So I'm going to multiply by 0 and divide by, well, excuse me, multiply by h and divide by h. I'm not dividing by 0. I'm just dividing by h, which is not 0. H is approaching 0. So if I take this expression and I multiply by h and I divide by h, you can see what happens. When I multiply by h and divide by h, now you know that nothing happens whenever you multiply by a number and divide by the same number. You still get the same thing back in return. So this equal sign is not egregious to write. But what has resulted now is an expression of the derivative. And we have assumed that our derivative exists. So this expression is something. In particular, it is the slope of the tangent line at the point of interest. So for the point of interest here, the slope of the tangent line is whatever the slope would be for the tangent line for the point, any point of interest. The expression that results from the derivative is going to be the slope of the tangent line at that point. So this guy here, in parentheses, is the derivative. It's something, whatever that slope is. And now we're multiplying it by h. But what are we doing with our limit? Our limit is as h approaches 0. So this expression, whenever we run the numbers on it, is going to be whatever number results from the derivative computation, which is just some number, and it's going to be multiplied by h, which is going to 0. And whatever number corresponds to the slope of the tangent line at the point of interest is whatever that number is, but you know any number times 0 is just 0. So what have we shown? We've shown that our limit of f of x plus h minus f of x as h approaches 0 is 0. And when this limit is 0, the limit and the function value are equal. And when the limit and the function value are equal, that's a criteria for continuity. So since our limit here has a value of 0, we know our function is continuous. And what's the big takeaway from going through this? If you have a derivative, then you must be continuous. So if you're not continuous, you can't possibly have a derivative.